So if you haven't tried this page, you should try it out. I think it's like page 23. Try it out first, and then you can compare your answers with mine. Or if you're like no idea how to do it, this is what this video is for. And if you don't know anything about magnetic flux, you can find a video about it. Mr. Gusson has a really good one, as per usual. He's a great explainer. Hopefully, we can make these problems make sense. So the first problem is like, I don't know how it's worded. It's just the flux through this loop of wire that's rectangular. This is kind of an interesting one because there's really two magnetic fields going through it. So as a reminder, magnetic flux, the equation on your equation sheet is equal to BA cosine theta. It might show up as like B dot A, or like there's like absolute signs for the first one, but this right here is a dot product, and that just means that if you take a dot product of two vectors, right, your magnetic field and your area, you get a scalar quantity. So magnetic flux doesn't really have direction, but it can be either positive or negative, and you can imagine that one of these is going to be positive and one of these is going to be negative. Now, I'm sure, like, I'm sure there's a way to tell if it's negative, because I'm pretty sure, like, you could say, well, the area vector is pointing out, and then this magnetic field is pointing away, so, like, it would be a negative quantity, but it doesn't really matter. You can choose which one is going to be positive, so you could say the one pointing into the page is going to be a positive flux, and then the one pointing out of the page is going to create a negative flux. You can decide that. But the point is that they're kind of fighting each other. This magnetic field is going to create a flux in the opposite like sign, like either negative or I'm explaining that wrong way. I'm going to say that again. One of these is going to create a positive flux. One of these is going to create a negative flux. They're kind of like fighting each other. If they're both in the same direction, they'd be both creating positive flux or whatever. So I would say the net magnetic flux is an equal one of these magnetic fields, I'll say like B1 times A1 minus B2, right? The other magnetic field times A2. So BA, right? Cosine theta, they're both like in the same, like, you know, like theta is 0, so we don't have to worry about like any angles or anything. So I can just start plugging in values. So B1, you could choose one of the magnetic fields. I know this one has a stronger magnetic field, so I probably want this one to be positive just so that at the end I get a positive number. Once again, it doesn't really matter though. So 2 Tesla times, and the area, it's not the area of the whole thing, it's just the area, like the half area, right? So this 20 by 20 square, that's the area of that flux, right? This individual, like, I don't know, half flux or whatever. So 20 centimeters, it's a square, so 20 centimeters squared, or I'll say 0.2 meters squared, minus, and we have B2 is 1 Tesla, right? So the other magnetic field pointing out of the page is 1 Tesla times 0.2 meters squared again. And that's why, you know, they're the same area, so I knew the magnetic fields are each piercing through the same area, so I knew that the 2 Tesla one is going to have an overall greater flux, and that's why I decided to make that one positive, because it has more magnetic field. So I think you just plug this in your calculator. I think it's 0.04 Tesla meters squared. That's the unit for magnetic flux. I'm pretty sure a Tesla meter squared is the same thing as a unit called the Weber. You know how like watt is the unit for power, but it's really just joules per second? It's that kind of thing. I like saying Weber because it makes me feel like I'm a scientist. Like, it makes me feel like makes you just feel cooler when I write Webers. Like, I have 0.04 Webers of flux. Doesn't really matter though. For number 2, so we have this circle thingy being pushed into this uniform magnetic field. I think it's into the page. It's out of the page. I'll just pretend it's out of it. It won't really change your answer, but why not? Out of the page. So this is 0.1 meter, right? It's a 10 centimeter loop. I'll just box this. All right, so it's asking, determine the magnetic flux before the loop is entered into the field. Well, before the loop is entered into the field, there's no magnetic field lines going through it because it's outside the field. I know for sure, so I guess I'll write 2 here. I know for sure for A, it's going to be 0 Webers because there's no field lines going through it. If I think about BA cosine theta, B is 0. My magnetic flux is 0. And even though B is 0.5 Teslas, remember this equation is saying what's the magnetic field through that area? Through this area, there's no magnetic field, even though that region is 0.5 Tesla. Okay, so halfway into the field, hopefully this isn't too bad when you're halfway, so I don't know, maybe change it to look like this. So when you're halfway through the field, it's uniform, so you know, it seems intuitive to say that this whole thing is 0.5 Tesla. So if this whole thing is 0.5 Tesla, this is only going to be a portion of it, but uniform means that everywhere it's 0.5 Tesla. So for 2B, you could just do phi equals BA, right? And B is 0.5 Tesla. The area is just half a circle, so it'd be pi r squared over 2. Pi, the radius is 0.1 squared over 2. I got for this one 0.00785. 0.00785 Webers. So yeah, hopefully that's not too bad. And then when it's fully into the field, then you just do the full area. So flux is equal to BA. It's equal to 0.5 Tesla times pi 0.1 squared. So I'm just using pi r squared for the full circle. It's really just 2 times this, so it's going to be 0.0157. 01. So 0.0157 Webers. All right. For this last one, it's saying if there's a magnetic field that points to the top of the page, draw, so in the positive y direction, draw a diagram for how you could have a loop get the maximum flux and the minimum flux. So if we were to draw this out, if I were to draw my magnetic field, to get the maximum flux, I gotta make sure that the area is kind of parallel with the magnetic field. So if I'd have to draw it like this. Now I know it looks perpendicular, like it looks like it's like kind of perpendicular to the magnetic field, and I guess you could think of it that way, but when I mean parallel, I'm talking about the area vector, which points up, right? Points like, it points to the normal of the area or whatever. It points like kind of in the direction the area is facing. All right, and then to get the least amount of flux, I know this is kind of scatterboard or scatterbrained whiteboard, but whatever. You would draw it perpendicular, right? So if you think about the area vector, it's going to be I keep drawing delta. It's going to be perpendicular. So this is how you get the maximum flux. If this is my loop, and if this is the field line, this is how you get the minimum flux, because none of them are going to be passing through the loop. So hopefully that makes sense. If you were to explain the angle, which is what the next part's talking about, you could just talk about how the angle between the area vector, which is pointing up, and the B field, which is pointing up, it's 0. So cosine theta, right, if you go back to this equation, when theta is 0, this is equal to 1. So you get phi is just equal to BA, right? It's like just cosine theta is equal to 1. But when the angle between it is 90, so the area vector is this way and your B field is this way, cosine theta, right, cosine 90 is 0, so you get no flux. So hopefully that kind of makes sense. Hopefully these problems weren't too bad. Let me know if you have questions. And yeah, thank you for watching.